Hello, chemistry of Earth and Space Science. Today, what we're going to do is talk about how to balance chemical equations. It's still the same day with my hiccups, so bear with me, please. I will do my best to make this sound somewhat logical. Okay, so we talked about what a chemical reaction was, going from reactions to products. For the next two lessons, we're going to deal with this concept of what's called the law of conservation of mass. And we're going to write chemical equations in a correct format that shows or models that conservation of mass during a chemical reaction. So what is a chemical equation? A chemical equation is something that describes a chemical change. The parts of the equation are, obviously, there are the reactants, the things you start with, and the products, the things you end up with. And then there's the yield sign in between. All this is a review from what was in the last video. The reactant is the thing that you start with before the reaction. It's usually written on the left side of the equation, left side of the arrow. The products, that's the new chemicals that are formed during the reaction, and those are written on the right side of the equation. So now let's focus on this next aspect of writing chemical equations, and that's the use of subscripts and coefficients. We've already dealt with subscripts. Okay. We know that the subscript is going to describe for us how many of that particular element are in a particular molecule. So for instance, when we say H2O, we know that that means that we have 2 atoms of hydrogen and 1 atom of oxygen. Easy enough. The subscript indicates how many of whatever's immediately to the left of that subscript. So what's a coefficient? A coefficient is going to be a number that's going to tell us how much of or how many of those molecules are going to be involved in a chemical reaction. The coefficient goes out front. Now this is kind of a weird font, but the 3 here in this situation indicates that this is 3 H2Os, which means there are 3 waters. That 3 is out front, in front of the compound's formula. What this means, if we have 3 waters, knowing that we had, hold on, I figure out what's jingling at me. See if that works better. Okay, sorry, had a little bit of noise. Okay, so 3 waters means that we have 3 water molecules, but since each water molecule had 2 hydrogens and 1 oxygen, this designation says that we have 6 hydrogens, 3 times 2 hydrogens, and 3 oxygen atoms, 3 times 1 oxygen atom. So that 3 out front, you're going to multiply through everything that is to the right of that coefficient, the number up front. So let's check a few. If I had the compound CaCl2, how many of each element is present? Well, we can tell that there's 1 calcium and 2 chlorines. Okay, we're on a roll. If we had barium sulfate, it's not a surprise and nothing complicated about the fact that we have a barium, a sulfur, and 4 oxygens. That subscript 4 on the oxygen only applies to the oxygen. Let's incorporate those parentheses. If we had NH4 2 C2O4, 4, since inside the parentheses there's one nitrogen and outside the parentheses there's a 2, that says that there are 2 nitrogens. So inside the parentheses there is 1 nitrogen and 4 hydrogen. And the subscript being outside of the parentheses says there's 2 of that combination, which means there's two nitrogens and a total of 8 hydrogens. And for the rest of the molecule, there's the 2 carbons and the 4 oxygen atoms. Now let's use our coefficients. Suppose I had 3 NH3. Now let me have the coefficient out front. Remember that 3 out front multiplies by through everything to the right of that coefficient. So that means we have 3 ammonia, 3 NH3s, which would say we have 3 nitrogens, and we have a total of 9 hydrogens. We've had 2 sodium chromates. Well, that would mean, again, that 2 outside, the coefficient out front, applies to everything to the right. And since sodium, Na2, there's 2 sodiums, times the 2. For the coefficient, I've got 4 sodiums. In Na2CrO4, I have 1 chromium, but since I have 2 of that molecule, I have 2 chromiums. And in the molecule Na2CrO4, I have 4 oxygens, but since I have 2 of the molecule, I have 8 oxygens. Last one, about as complicated as it can get. What if I had 4 aluminum carbonates? Okay. In the formula for aluminum carbonate, I have 2 aluminums. But since I have 4 of the aluminum carbonate, I have 8 aluminum atoms. Keep moving across. In the compound of aluminum carbonate, I have 3 carbon atoms. I have 1 carbon atom per carbonate. For this molecule to be made, I need 3 carbonates. So that means I have 3 carbon atoms. Times the 4 aluminum carbonates, that means I have 1 times 3 times 4, or 12 carbon atoms. And then finally, in aluminum carbonate, in the carbonate, there are 3 oxygens. But I have 3 carbonates in the molecule. So I have, in each aluminum carbonate, I have 9 oxygen atoms. And since I have 4 aluminum carbonates, I have 4 times that 9, or 36 oxygen atoms. So one of the skills we're going to have in order to balance equations is the ability to count the number of atoms using our subscripts and our coefficients. Here's a cute little animation showing hydrogen reacting with oxygen to make water. 2 hydrogen atoms, those are the green doubles, finding an oxygen, and when they combine in just the right way, the oxygen atom is pulled apart, oxygen molecule is pulled apart, and it takes away with 2 different H2Os. That's a chemical reaction. You can see the amount of the elements don't change. I start with 4 greens, I end with 4 greens. I start with 2 reds, I end with 2 reds. I start with 4 hydrogens, I end with 4 hydrogens. I start with 2 oxygens, I end with 2 oxygens. So that whole idea of having the amount of material not change is referred to as the conservation of mass. In a chemical reaction, and if you've taken physics already, in a chemical reaction, matter is neither created nor destroyed. It's very similar to the law of conservation. Energy cannot be created nor destroyed. It can only change type. Well, here, mass will not change. The total amount of mass will not change during a chemical reaction. Whatever the mass is you start with will be same exact mass as you end with. What that means is the number and types of atoms going into the reaction must be the same as the ones coming out. So if I were to count up the atoms of each element on the reactant side of the yield sign and compared it to the total number of atoms of each element on the product side, they should be the same in order for a chemical reaction to be what's called balanced. If the chemical equation is written in such a way that the number of atoms on the reactant side equals the number of atoms on the product side, we call that a balanced chemical reaction. So let's look at an example of an unbalance. So here we have methane, CH4, reacting with oxygen to produce carbon dioxide and water. So when we start, we have one methane and one oxygen. And if we count the different atoms, the carbon is black, so we have one carbon atom. The hydrogens which are attached to the methane are green. So I have four greens. And oxygen is diatomic. So I see that oxygen atom is red. I have two oxygen atoms. When this reaction is done, I still only have one carbon atom. That's great. But I notice that I have two hydrogens instead of four and three oxygens instead of two. So what apparently has taken place here with this equation, it's not balanced, is we've lost some hydrogen atoms and we've gained some oxygen atoms, and that's not allowed. We have to have the same number of each atoms on both sides of the reaction. So the way we deal with this is a lot like what we did back in ionic bonding, is on each side I could duplicate the molecules that are there in order to make everything balance out. So for instance, since I see the left-hand side, the reaction side, I have four greens. I want four greens on the right-hand side. So I could add two more greens, but I can't just add greens. The greens are part of this thing down here, this water molecule. So what I'm going to do is I'm going to add another water molecule. I now have two water molecules. I have two water molecules. That means now I have my four greens, just like I had over the reaction side. But now I have four reds, or four hydrogens. So I have too many hydrogens on the product side. Now I can't remove anything, but I can go over to the reactant side and say, well, let me add oxygen atoms. But I can only add oxygen atoms as the oxygen molecule. I can duplicate this thing, this oxygen molecule again. So I do. Let's duplicate that. Now I have two oxygen atoms. I have one methane molecule. I have two oxygen molecules, diatomic oxygen molecules. I have one carbon dioxide molecule and two water molecules. I have four hydrogens. I have one carbon. I have four oxygen atoms. I have 1, 2, 3, 4 oxygen atoms. The equation is balanced. This would be the way I would write the balanced equation for this reaction. This process of adding coefficients in front of the molecules is the balancing equation process. So here's some conditions or rules of the game. First off, we know that matter cannot be created nor destroyed. So we can't just make new atoms. We can't do that. We can't just add atoms just because. We can duplicate the molecules or atoms that are there, but we can't just add a single atom or anything like that. And we can also not change the subscripts that are part of the molecules. Once you've written the formula for the compound, you must leave it alone, not change the subscripts, only add coefficients out front to show an additional number of each one of the components that were reactants or products. The coefficients, we said, only go in front of the chemical formulas, never in the middle of the formula. That's kind of weird, but I've seen that happen before. And some other helpful things when balancing equation. First, try taking care of the big formulas first. Okay, something that has more complicated arrangements that you can just see that, like example we just had where we had 4 hydrogens on one side and 2 hydrogens on the other side. We could do what we can to change that one element because that one element is in 2 different compounds, one on the reaction side and one on the product side. So make the coefficients work. When trying to make things fall into place, if an element is in a lot of different compounds, try to push it towards the end, towards the last part, and hope that it all falls together nicely. Another thing is sometimes, not all the time, but sometimes you can count the polyatomic ion as entire polyatomic ions, and that's only assuming that the polyatomic ion doesn't change from one side to the other. It's sulfate on one side and all the sulfurs are in sulfate on the other side, in which case you can just count the sulfates rather than the atoms. It's safer to count the atoms, but sometimes you can get away with counting the polyatomic ions. And then finally, there's no one way to balance an equation. Absolutely not. Everybody has their own ways. Some equations are darn right near impossible to balance. And you might actually get to the point where those of you who are math-minded might consider using systems of equations to make it work. I think that's a lot, but you know what? I've seen crazier things happen. My suggestion is first take care of the elements that are in one compound on each side and balance them out first. And gradually work yourself up until finally you're just at the end saying, well, now I need to adjust the sodium atoms. How many more do I have? Okay, so let's look at some examples. So here is a chemical equation for the production of ammonia. NH3 is ammonia, or nitrogen trihydride. It's made by reacting hydrogen gas and nitrogen gas together to make the ammonia. And this is not balanced. How can I tell it's not balanced? Because if I look at number of each atoms on the reactant side and the product side, on my reactant side, I have, let's see what color I can use. Too, the dark red's too much. Okay, on the reactant side, ooh, my. Oh, it's going to be one of the days, isn't it? Oh, it's super sensitive today. I can't have that. Let me get rid of that real fast. Sorry about that. I ain't a little sensitive. Try that one more time. Okay. So the nitrogen here, there's 2 of them. So I have 2 nitrogen atoms. And on the left-hand side, I also have 2 hydrogen atoms. And I can't change the formulas to make things add up nicely, but I have 2 hydrogen atoms. Let's go to the product side. On the product side, if I look at ammonia, that ammonia, again, I can't change the formula, has 1 nitrogen and 3 hydrogens. So right now I can tell it's not balanced because I see that I have an inopportune number. But let's fix something. Let's fix those nitrogens first. What number can I put out front here that would make there be two nitrogen atoms on the product side? If you said 2, you're right. So now that I put the 2 out front, I have 2 nitrogens on both sides. Fixed. My nitrogen atoms are happy and content. But in doing so, I now doubled the number of hydrogens from 2 to 6. So I made the hydrogens worse. But nitrogens are good. I see right here that there's a space for me to put a coefficient out there. So if I choose, the circles were just there to say we can't change the formulas. Okay. If I now try to come up with a coefficient to put out front, what times 2 is 6? If you said 3, you're right. So now when I put that 3 out front in the coefficient spot, I now have 6 total. I had hydrogen atoms and 2 nitrogen atoms. So this, my friend, is and that's not working well, and I wanted to draw a smiley face, but I guess I'm not going to because not cooperating. But you know, I'm pretty stubborn, so I'm going to give it one more shot. One more time. Smiley face. Well, he's fat and happy. Everything's cool. So this equation is balanced. What does it look like? Using bubbles or dots or whatever circles you want. I have 1 nitrogen, so 2 blues. I have 3 molecules of hydrogen, H2, H2, H2. And I have 2 molecules of ammonia, a blue and 3 hydrogens, 3 greens. And if I count them up, I got 2 blues on each side, and I got 6 greens on both sides. This would be a nice visual to tell me that this is balanced. Okay, let's try another one. KClO3, potassium chlorate, decomposes to make potassium chloride and oxygen gas. So let's do our tally and take all of our different elements, potassium, chlorine, and oxygen, and start adding them up. So on the reaction side, in the potassium chlorate, I have 1 potassium, 1 chlorine, and I have 3 oxygen atoms. On the product side, I have 1 potassium. Yay, that's the same as I have on the reaction side. I have 1 chlorine. Yay, the same as I have on the reaction side. But I only have 2 oxygen atoms. So it looks like I've lost an oxygen atom. And we already know that we can't lose matter. So how do we fix this? What can we put as coefficients in front of the 2 different compounds? The potassium chlorate that has the oxygens and the oxygen molecule that has the oxygens to make there be the same number on both sides. Well, if I put a 2 out in front of the potassium chlorate, now I have 6 oxygen atoms. And if I put the 3 out in front of the oxygen, O2, well, now I have 6 oxygen atoms there, and it looks fine and dandy, but I've also messed up my chlorines because I put the 2 out front. Then now I have 2 potassiums and 2 chlorines. But luckily, we can fix that because on the product side, we have a potassium chloride, which has 1 potassium and 1 chlorine each. So if I just put a 2 out there, I've got 2 potassiums and 2 chlorines, and we're balanced. Not a very happy, but it's a happy. Okay, let's try a few more. This time we're going to do just the tallies. So, if I have and I kind of like to do this. I'd like to put the tally in the middle. So if I say I've got irons here, and I've got oxygens. On the reaction side, I have 1 iron and 2 oxygens. And on the product side, I have 2 irons and 3 oxygens. So I can tell. I said, if something's by itself, like this iron is, I want to do that last. So let's take care of the oxygens, just like we did on the last one. So if I put a 2 here, ooh, got my spiker going. If I put a 2 there, two out front here, now I've got 4 irons and 6 oxygens. But I can balance out my oxygens by putting 3 here. Now I've got 6 oxygens. Oxygens are good. Iron's not so much. So I'm going to go ahead and put a 4 out here. So when this thing is balanced, I have 4, 3, and 2 as my coefficients, which would be the correct coefficients for this particular equation. That's why I try one that's a little bit harder. Again, I tend to like putting my elements right down the middle. So I'll do carbon, hydrogen, one oxygen here. Why don't you want to play? Okay. New life. And oxygen. Okay. On the left-hand side, the reaction side, I have 2 carbons. On the left-hand side, the reaction side, I have 6 hydrogens. On the left-hand side, the reaction side, I have 2 oxygens. On the product side, I have 1 carbon dioxide. Sorry, I have 1 carbon dioxide, so I have 1 carbon. I have 2 hydrogens, because I have 2 waters, 1 water. And I have a total of 2 plus 1, or 3 oxygens. So I can tell you right now, I'm not going to fix oxygens first, because there's a lot of combination between the 2s, and the 1s to make that balance out. So I'm going to start by fixing the carbons. So if I put a 2 out here, that makes me have 2 carbons, but now my oxygens have messed up. I now have 4, 2 plus 1, I now have 5. I made that worse. Let me make it even worse. If I put a 3 in front of the water, now I have 6 hydrogens. But now I have 4 plus 3 times 1, 3. I have 7. That's a terrible 7. Okay, I have 7 oxygen atoms. Okay, I'm kind of messed up here. There's no coefficient I can put out in front here to make it equal 7, but because I can only use whole numbers. But let's just spend time for a second and say, what could I put there? What if I put 3.5? 3.5 would be 7 times 2 is 3.5, right? And that would work. However, I can't have whole numbers. I can't have decimal numbers. I can only have whole numbers because I can't have a fraction of a molecule. So what I'm going to do is take all my coefficients and multiply them times 2. So the 1 becomes 2. 5.5 becomes 7. The 2 becomes 4. The 3 becomes 6. And if I erase this mess, I get the correct coefficients to be 2, 7, 4, and 6. So the coefficients are not going to be always very simple, like 1s, 2s, and 3s. But with a lot of patience, you should be able to get the right balanced chemical equation. So that's the end of part 1 of balancing chemical equations. I'll be back in a minute with part 2.